I lost real money without running anything. I'm Captain Flasky Boy, a software developer with over 15 years of experience. Over the last few months, I've been developing a fully autonomous trading application. Let's talk about the current iteration of the autonomous trading application. From the very start, I wanted to build an application that could be run and deployed via a Docker container. The initial idea was to create a template that we could deploy to the cloud where it could run the entire day making market orders. To deploy the application to the cloud, I started using DigitalOcean Droplets. At the time, I thought this would be a cheap way to develop and eventually run my autonomous trade bot. I picked a low-cost droplet and assumed that if I turned the bot off, the costs would stop as well. Then, about a month later, the bill arrived. DigitalOcean charged me $7.42. This wasn't good. The autonomous trading application was designed to be a template. My overall plan was not to develop a single trade bot, but potentially hundreds of them. With each new instance being spun up, the cost would start to compound. $7.42 a month could quickly turn into $742 a month per each new autonomous trading instance if I did not do something now. We are starting this episode by deleting our DigitalOcean droplets. They are too expensive. Instead, we are pivoting to a managed cloud database for $15 a month and a serverless architecture, the Jamstack.
Wait, isn't $15 a month more than $7, sir? I may be a trading bot, but even I can detect when the maths look sus.
On the surface, this looked stupid. Why would I replace a $7 bill with $15? The $7 bill was only cheap because I was looking at one bot, and this project was never designed to stop at one bot. So naturally, the first step in saving money is spending more money on a managed database in DigitalOcean. Okay, so back to Jamstack. While I was messing around with serverless functions in DigitalOcean, I kept noticing a tutorial for something called Jamstack. DigitalOcean had been shoving it in my face for over a month, and eventually I gave in and clicked on it. That is when I stumbled onto something important: static websites. So, what is a static website? A static website is basically a website that does not need a server constantly running in the background to build every page on demand. A simple example would be something like Google Sites. You create the pages you need, add your text images, buttons, and links, then publish it. When someone visits the site, they are mostly just viewing pre-built pages. It's just a lightweight front end that displays information, and that is when it clicked. The autonomous trade app does not need a full web application running 24 hours a day just so I can look at what the bots are doing. The website can be static, the logic can live somewhere else, and suddenly, the expensive little Docker container started looking very replaceable. So back to Jamstack. Jamstack is basically a way of building websites where the front end stays simple, fast, and mostly static, while the heavy logic lives somewhere else. For the autonomous trade app, the dashboard does not need to think, make decisions, or place orders. It just displays information, while serverless functions do the real work in the background. Let's look at the current architecture. Everything is bundled into one Docker container and hosted on a DigitalOcean droplet. The user interface, bot logic, and database connection all live in one place. That makes it simple to run, but expensive to scale. Every new bot risks becoming another always-on container. Let's look at where the architecture is heading next. The architecture is moving away from one always-on droplet and into three cleaner parts. The bot logic moves into serverless functions, so it only runs when needed. The data moves into a single managed database for watch lists, orders, positions, and decisions. And the website becomes a read-only static front end that simply displays what the bots are doing. So now that we have discussed the problem, the costs, the architecture, and my obvious weakness as a fleshy meat-based developer, I think it's time we get to work. The first thing I did was set up a managed cloud database. Then I downloaded DataGrip, which is a database interface made by the company JetBrains. As a PyCharm user and a genuine fan of JetBrains tools, DataGrip made perfect sense, especially because it is now free for non-commercial use. And after around 30 minutes of fighting connection strings, ports, SSL settings, and my own sanity, I finally connected to the cloud database. I then validated my connection by typing a few basic SQL commands.
Next, I opened Alpha Terminus and began writing the code to define the autonomous trade app's database structure.
As I started building the database in the background, there was a few things I needed to consider, because all the share one Alpaca account. Alpaca Markets is the brokerage platform the autonomous trade app will use to actually place trades. It gives us an API for creating orders, checking positions, and pulling account information, which is exactly what we need for automated trading. The problem is, Alpaca only sees one account. It does not know that I have multiple bots with different strategies, personalities, and questionable decision-making. Alpaca can tell me an order was placed or a position exists, but it does not automatically know which bot made that decision. And for this project, that is a problem, because each bot needs to be tracked separately. So, while building the database model, we need to create something I am calling the attribution layer. This is the part of the system that links every decision watchlist, order, and position back to the bot responsible for it. Without this layer, all the bots would become one messy pile of trades, and I would have no idea who was performing well and who needed to be unplugged. The attribution layer also lets us track limits and performance per bot. One bot might have a weekly investment limit of £1,000, while another might be more restricted because it has the financial instincts of a confused toaster. This is why the managed database matters. Alpaca executes the trades, but our database explains who did what, why they did it, and whether it was actually a good idea. The managed database is not just for one version of the autonomous trade app. It needs to become the shared backend for 3 different trade applications that all interact with the system in different ways. Here the code starts with a simple test bot configuration. We give the bot a name, a description, a unique slug, and a starting paper cache balance. That slug is important because it becomes the stable identity the rest of the system can use. The name can change later, but the slug gives the database and functions one reliable way to know which bot they are dealing with. Then we create the actual trade bots table. This is the foundation of the attribution layer. Every bot gets a unique ID, a display name, a unique bot slug, a paper cache balance, and a created timestamp. A clear record that says, this bot exists, this is its identity, and this is the cache it is allowed to start with. To model and develop the database, I started by writing the code locally using Python and the psycopg adapter. Yes, apparently it is pronounced psycopg, which is exactly my level of emotional stability. Psycopg is one of the most popular Postgres adapters for Python. It lets the app connect to Postgres and run SQL, which is useful when you are trying to build a serious trading system. And just like that, we have finished modeling the database. Here we can finally see the database model taking shape inside DataGrip. At the center of everything is the trade bots table. This is the identity layer. Every bot gets its own name, slug, cache, balance, and description, so the rest of the system knows exactly which bot it is dealing with. From there, everything links back to that bot through the trade bot ID. Orders, decisions, watch lists, thoughts, comments, and cache ledger entries all connect back to the correct bot. That means even though multiple bots can share one Alpaca account, the database can still tell us who did what. We can track watch lists, orders, positions, cache movements, and closed lots for profit or loss. I prefer my financial mistakes properly labeled. Okay, so let's focus on the trade bots and bot orders tables. I have run the bot a few times to seed the database with test data so we can see how the attribution layer works in practice. In the trade bots table, we have the core identity fields I mentioned earlier, the unique internal ID, the readable bot name, and the bot slug. Then in the bot orders table, every order gets linked back to one of those bots using the trade bot ID. It also stores the Alpaca order ID, which is the order reference generated by Alpaca markets. On top of that, I added a client order ID, which gives us another way to trace the order from our database to Alpaca and back again. Okay, now I want to move back to the CDN and static website part of the development. A Jamstack-style web application normally needs a few key pieces. First, it needs somewhere to host the static website. Second, it needs a CDN to serve the page's assets and data quickly. Third, it needs a data source, like a JSON file, API, or storage layer. And finally, it needs a way to update that data without turning the website back into a full backend application. To do this, I am going to use a slightly unconventional setup. Google Sites will host the read-only TradeBot dashboard, while Google Drive acts as a simple storage layer for cached files like images, assets, and summary data. Then DigitalOcean serverless functions will continue doing the real backend work. They can run on triggers, process the latest TradeBot data, and use the Google Drive API to push updated cached files into the drive. Technically, Google Drive is not a proper CDN, it is file storage. But for this version of the project, I am treating it like a lightweight storage and publishing layer for the static dashboard. To start building the dashboard, I did what any responsible software developer would do. I asked ChatGPT to design it for me. I got it to generate a mock dashboard with the kind of features I wanted to see, like total bot count performance, stats, watch lists, recent decisions, and a leaderboard so the bots can publicly compete for dominance. Then I embedded that mock dashboard into a Google Sites page using the embed code feature. This gave me a quick visual prototype and helped me figure out what the final dashboard should actually look like before working on the serverless functions. Then I started reworking the existing serverless functions so they could properly interact with the managed database. Instead of just running isolated bits of logic, the functions now needed to create records, update bot data, store decisions, track orders, and keep everything linked back to the correct trade bot. While reworking the serverless functions, I needed each one to write back to the managed cloud database. That sounded simple enough right up until DigitalOcean reminded me that simple is not really the theme of this episode. When you create a DigitalOcean serverless function, it comes with a limited set of pre-installed Python packages and libraries. Unfortunately, psycopg was not one of them. Now, I could have gone down the rabbit hole of building a custom environment, packaging dependencies, and slowly questioning my life choices. But then, I noticed something already available, and that was DuckDB. It gave me another route to connect the serverless functions to the database and keep the project moving. Now, let's move on to the storage layer and build the dashboard summary pipeline for the TradeBot system. To make this static website feel dynamic, we need to generate a summary file that contains everything the dashboard needs to display. That means the latest bot activity, watch lists, orders, positions, leaderboard data, and enough performance information to show what each TradeBot is doing. To do this, I developed a Python script which generates a summary file locally. At first, I thought getting that file into Google Drive would be straightforward, but there needed to be a secure way for the serverless function to update the cached dashboard data. Eventually, I was forced to build a Google Apps script endpoint that accepts the data, checks a token, and overwrites the file in Drive so the dashboard can read the latest version. If enough people are interested, I can make a follow-up video on the full setup. But the short version is this. A DigitalOcean serverless function now triggers a Google Apps script endpoint, which updates the cached dashboard file in Drive. So now we have a DigitalOcean serverless function that accepts a Google Web App URL endpoint and can run on a trigger as often as we need. If we open Google Drive, we can see the result. A populated cached file is sitting there ready for the dashboard to read, which means the dashboard summary pipeline is finally working. Now we can move on to the dashboard itself, which is the part the viewer actually sees. Google Sites does not need to run any trading logic. It just needs to load the cached summary file. Let's launch Alpha Terminus and start building the dashboard. We already decided that Google Sites would host the dashboard, but a normal Google Sites page is a bit too static on its own. So, to make it feel more like a real application, I used the embed option and placed a Google Apps script web app directly inside the page. Let's take a look at the first iteration of the dashboard. At this stage, the goal is not to make it perfect. The goal is to prove the structure works. We need to see if Google Sites can host the page, if the embedded app script can load properly, and if the dashboard can read the cached summary file from Google Drive. When we load up the page, we can see the first version of the dashboard starting to come together. At the top, we have the leaderboard, and below that, the bot roster. Right now, there are 2 bots showing Jemmy Chan and the test bot I've been using during development. I don't want the bots to feel completely static, so each one will eventually have idle blinking and talking animations that we can build on later. You can also click each bot in the roster to open more details, viewing its description, watch list, latest orders, and latest comment. For example, Jemmy Chan's latest comment shows the reasoning behind its purchase of Oracle shares. Next, I wrote another Google Apps script web app to generate a Sprite manifest. The idea was simple. The script checks the cached summary file to see which bots exist, then searches a Google Drive folder for a matching 32 by 32 pixel sprite for each bot. If the sprite file name matches the bot slug, the dashboard can automatically load the correct character. That means I don't have to manually hardcode every image into the front end. The dashboard can read the bot list, search the Google Drive Sprite folder, find the matching 32 by 32 pixel image, and attach it to the correct bot profile. The only real problem was permissions. Google Drive would let the dashboard find the files, but it would not display them until the sprites were publicly accessible. So every image in the Sprite folder had to be shared with the web, or set so anyone with the link could view it. Once that was fixed, the system finally worked. And if we look at the next iteration of the dashboard, we can see the sprites loaded. For development, I reused the Jemmy Chan sprite created for the old Droplet version of the application. Once that worked, I reworked the test bot sprite so I could check that the system was actually matching each bot correctly and not just turning the entire roster into a Jemmy Chan fan club. I also updated the trade GPT instructions and endpoints so it can now work with the managed cloud database. At this point, I think we are up to around 21 endpoints, which is becoming less of an API and more of a small government department. Now, Trade GPT can read and write through the same managed database as the other bots. That means it can have its own bot slug, its own watch list, its own records, and its own place in the TradeBot roster. And after a little bit of pixel magic, we now have 3 bots showing inside the dashboard. Finally, I decided to add myself Captain Flasky Boy to the dashboard as a baseline. Just one fleshy developer making trades manually. The idea is simple. If I am building a roster of autonomous trade bots, I need something human to compare them against. So that means me, Captain Flasky Boy, becomes the control group. That brings us to the end of this rebuild. We started this episode with a problem. The old Droplet-based setup worked, but it was too expensive to scale. Every new bot risked becoming another always-on container, and that was not going to work if the plan is to build an entire roster of autonomous trade bots. Instead, we deleted the old setup and started moving towards something cleaner. A managed database to track every bot, serverless functions to run the actual logic only when needed, a Google Drive to hold the cached dashboard data, and Google Sites to display everything. And now, for the first time in months, we have our modular dashboard and can create all the trade bots we want. In the next few episodes, we will be moving away from pure development and getting closer to the real goal of this project, which is building wealth, creating financial freedom, and seeing whether these trade bots can actually help us get there. And if you have made it this far, watching this absolute mess of a channel slowly turn into a real project, then from the bottom of my heart, thank you for watching. I genuinely appreciate it, and hopefully I will see you in the next episode.